Swayam Prabha. Digital India. Educated India.
Welcome back to lecture number 4. In this lecture, we are going to discuss about how the ideal vapor compression refrigeration cycle has been modified. Especially, we will be studying about the effect of subcooling, superheating, and how the ideal vapor compression cycle differs from the actual. How the actual cycle, vapor compression cycle, deviates from the ideal vapor compression cycle. So this is the schematic of the ideal vapor compression cycle, which we had already discussed in the lecture number 2. To just summarize, we have there are 4 major components of ideal vapor compression cycle: compressor, condenser, expansion device, and evaporator. So the refrigerant is compressed isentropically, that is the reversible adiabatic process, from 1 to 2. Then isobaric heat rejection process takes place in the condenser, that is 2 to 3. During the phase change, the process is isothermal. Then 3 to 4 is throttling process, in which enthalpy of the substance remains the same, that is H3 equal to H4. And the low pressure liquid refrigerant, which is entering the evaporator, it takes the heat from the space where cooling is required and gets converted into vapor, and the vapor is again compressed in the compressor, and the cycle continues. So during the process 4 to 1 also, it is isobaric heat addition process. Of course, during the phase change, the process is isothermal. So this is the temperature entropy diagram and the pressure enthalpy diagram, which shows the 4 processes: 1 to 2, 2 to 3, 3 to 4, and 4 to 1. If we see in the ideal vapor compression cycle, we assume there is no losses, there is no pressure drop, all those things and all. So whenever we say isobaric process, the pressure of the working substance before the refrigerant entering that particular component will be equal to the pressure of the substance which is leaving the particular component. That is, we say T1 is equal, if we take this the diagram, T1 is equal to T4, condenser pressure will be equal to P2, which is equal to P3, T1 equal to T4 equal to, condenser temperature T2 equal to T3 is equal to Tc, and the evaporator temperature is T1 equal to T4 equal to Te. Similarly, if you see the pH diagram, P1 is equal to P4 and P2 is equal to P3. If we take the actual cycle, if we take in the actual process, what happens is, if we take the high pressure side, that is the condenser side, the condenser side is the high pressure side and the evaporator is the low pressure side. So what happens, the temperature of the heat sink, that is normally it is at a lower temperature than the temperature of the condensing temperature, in order to facilitate the heat transfer process. So similarly, the temperature of the low temperature heat source, that is more than the temperature of the refrigerant which is evaporating. So what happens when we say the concept of subcooling? Why it is called subcooling? The refrigerant is cooled to a fewer degree, to a temperature less than the temperature of the saturated condition, maybe 5 degree or up to 10 degree. Normally a 5 degree subcooling is preferred. So what happens, the liquid refrigerant, which is after the condensation process, after the phase change process, the liquid refrigerant is cooled to some degree in the condenser. This process takes place by providing additional surface area for the heat transfer to take place. So this process does not take place in a separate component or a separate device. It takes place within the condenser. Extra or additional heat transfer surface area is provided to facilitate this process. So the temperature, the refrigerant is cooled to a few degree, and when it leaves the condenser exit, it will be in subcooled condition. So if you look at the diagram, this is the TS diagram. So without subcooling, the process is 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Similarly, here 1 to 2, 2 to 3, 3 to 4, 4 to 1. 3 dash and 4 dash represents the portion which is due to subcooling. So let me write subcooling. This process takes place within the condenser by providing additional surface area for the heat transfer to take place. Surface area for heat transfer to take place. So what happens? The temperature of the substance will be less than the saturation temperature. So if you see the diagram, this is T3. This is T3, which is nothing but the condenser temperature. This is the condenser temperature. And this is T3 dash. That is nothing but the temperature of the liquid refrigerant after the subcooling process is completed. In the previous lecture, I was explaining about, for example, if we take the temperature, condenser temperature is 40, and after subcooling the temperature is 35. So the degree of subcooling is 5 degree. That is 40 degrees centigrade minus 35 degrees centigrade. So let me explain here. So degree of subcool. Degree of subcool is subcooling is, this is nothing but T3 minus T3 dash, which is nothing but T3 is nothing but condenser temperature minus T3 dash. So refer TS diagram. This is based on refer slide. I think previous slide is 5. Okay, so refer slide 5. TS diagram. Refer slide number 5. TS diagram. So this T3 minus T3 dash is the degree of subcooling. Now, after the subcooling process, the refrigerant is expanded, that is throttled. That is the isenthalpic process. So where H3 dash will be equal to H4 dash, because the enthalpy remains constant. Whether the refrigerant is subcooled or not, after condensation process, when the refrigerant enters the expansion device, it undergoes isenthalpic process. So it is H3 equal to H4 without subcooling, and in case of subcooling is H3 dash equal to H4 dash. So the line will be perpendicular to the x-axis, which is enthalpy on a pH diagram. So here without subcooling, the cycle is 1, 2, 3, 4. Okay. So cycle is 1 to 2, 2 to 3, 3 to 4. With subcooling, cycle is 1 to 2, there is no change. Instead of 3, it will be 3 dash. Instead of 4, it will be 4 dash. It will be 4 dash. So 1, 2, 3 dash, 4 dash is with subcooling. How does it impact the system performance? So subcooling, first of all, subcooling will ensure that the liquid refrigerant is entering the expansion device. Liquid refrigerant, pure liquid only is entering the expansion device. It prevents the vapor formation in the liquid line. It prevents the the formation of vapor bubble. It prevents the subcooling, prevents the formation of vapor bubble in the liquid line. It ensures that only liquid enters the expansion device. During the expansion process, there are chances of some liquid getting flashed into vapor. And of course, that vapor content also will be less when it is entering the evaporator. Maximum amount of liquid will enter the evaporator, which will be ensured by the subcooling process. How does it impact the COP of the system? If we take the diagram, if you have a subcooling process, the subcooling process reducing the losses due to throttling. It reduces the losses due to throttling. That is another advantage of subcooling process. If you see the refrigerating effect, if you calculate the refrigerating effect, that is H1 minus H4. Without subcooling, the refrigerating effect is H1 minus H4. That is, this is H1. I will explain this portion with the pH diagram. This is H1 and this is H4. So QE is equal to mass flow of the refrigerant into H1 minus H4. This is without subcooling. Without subcooling. And with subcooling, QE is equal to m dot R into H1 minus H4 dash. That is with subcooling. So let me go here. So this is H4 dash. This is without subcooling. This is with subcooling. So it is clearly inferred from the pressure enthalpy diagram. The refrigerating effect increases. This is the refrigerating effect without subcooling. That is H1 enthalpy at 1 minus enthalpy at 4. This is QE, this difference. And this is here QE is equal to H1 minus H4 dash. Here Q. So this is the refrigerating effect increases. COP is equal to QE by work of compression. So with subcooling, the refrigerating effect increases. Therefore, COP also, since QE is in the numerator, if the numerator is increasing, the ratio also will increase, COP will increase. So the coefficient of performance of the vapor compression cycle will increase. So this is the impact of subcooling. Always it is desirable to have some amount of subcooling, like normally it is the degree of subcooling is taken as 5 degree. Like if the condenser temperature is 45, then the temperature of the liquid refrigerant leaving after subcooling will be in the range like 38 or 40, so that there is a 5 to 7 degree of subcooling. Second one is superheating. What is the effect of superheating? The temperature of the low temperature heat source, normally it is at a higher temperature compared to the evaporating temperature of the refrigerant. So because in order to facilitate the heat transfer, so due to this, what happens, the refrigerant, it is desirable to have a few degree of superheating when the refrigerant is exchanging heat with the refrigerated space due to the heat transfer between the refrigerant and the refrigerated space. Like how it is desirable to have few degree of subcooling, it is desirable to have few degree of superheating. This process takes place in the evaporator. So there is another superheating that is due to when the refrigerant leaves the evaporator, when it travels through the condenser, through the piping, through the pipelines, there are chances of the heat transfer between the refrigerant and the environment and the surrounding environment, due to which the refrigerant would be heated to the superheated condition. Of course, the second case, the one which I explained now, it will not increase the refrigerating effect or the performance of the system. Whereas if the refrigerant is superheated to few degrees due to heat transfer between due to heat exchange with the refrigerated space, the refrigerating effect will increase. Of course, the COP increase, whether the COP will increase or decrease depending upon the percentage increase in the work of compression, and also it depends upon the nature of the working fluid. Let me explain this superheating. So here 1 dash refers to the saturated condition of vapor, that is, and 1 is the superheated condition of the refrigerant vapor at the inlet of the compressor. Then 1 to 2 is isentropic compression. Then we have 2 to 3 this condensation process, 3 to 4 throttling, and 4 to 1 dash is again, it is isobaric heat addition process. So superheating is, first one is heat transfer with the refrigerated space. How this is possible? Because the temperature of the heat source, it is higher than the refrigerating, than the evaporating refrigerant. So it is possible to superheat refrigerant vapor to a few degree, not to a larger extent, to a few degree with the refrigerated space. If this type of superheating takes place, then this increases the refrigerating effect. Whether it increases the specific volume of the refrigerant at the compressor inlet, the specific volume. At compressor inlet increases. So when the specific volume at the compressor, the compression ratio will increase. Work of compression also will increase. However, the ratio will increase or decrease if the increase in the work of compression is less significant or less than the increase in the refrigerating effect. The COP of the system will increase. COP of the system will increase. Of course, it depends upon the nature of the refrigerant also. It depends upon the nature of the refrigerant also. COP may increase or decrease, increase or decrease depending on the nature of the working fluid. So the second one is the second type of superheating is the transfer. Heat transfer. Heat transfer with the heat transfer with the surrounding. Heat transfer with the surrounding when the refrigerant passes through the pipelines. Passes through the pipelines. This type of superheating will not increase the refrigerating effect. Will not be increasing the refrigerating effect. So here the degree of superheat is 1- to 1. 1- to 1. Again here this is the evaporator temperature. This is the condenser temperature. This is the degree of superheat. So the T1 minus T1 is the degree of superheat. Degree of superheat. It is desirable to have some degree of superheat, especially due to the heat transfer. If the heat transfer is between the working substance and the refrigerated space. Refrigerated space. So that will also that is desirable, like similar to the degree of subcooling. Degree of subcooling. So this is the TS and diagram and the pH diagram, which shows the combination of subcooling and superheating. Subcooling and superheating. So here if you see 1 to 2 is compression, then we have condensation, 3 to 4 is throttling, 4 to 1- is evaporation. So 1- to 1 is superheating process and 3 to 3- is subcooling process. 3 to 3- is subcooling process. Without subcooling, the throttling process is 3 to 4. With subcooling is 3- to 4-. So 3 to 3- is subcooling process. 1- to 1 is superheating. 1- to 1 is superheating. Superheating process. So similarly, this can be seen on the, this is from 1- to 1. The refrigerant is superheated due to its heat transfer with the refrigerated space. And 3 to 3- is the subcooling process. Subcooling process. Before I conclude this lecture, let us compare the processes of an actual cycle, how it deviates from the ideal vapor compression cycle. So this is the pH diagram which shows the actual cycle and the ideal cycle. So the ideal cycle is shown in the with a solid line. Okay, the solid line Solid line represents ideal cycle. And dashed line, this dashed lines represents actual cycle. It represents the actual cycle. So if you see the diagram, so this is the ideal cycle 1 to 2, then 2 to 3. 2 to 3 is isobaric heat rejection process, 3 to 4 throttling process, and 3 dash to 4 dash with subcooling. 3 to 4 is without subcooling. 3 to 4 is without subcooling. Without subcooling. 3 dash to 4 dash is with subcooling. With subcooling. So here if you see similarly we can plot this process on a temperature entropy plot. So if you see the type of compression between the ideal and the vapor, the actual process, in ideal case it is perfectly an isentropic process. So the line process 1 to 2 is perpendicular to the x-axis on a TS diagram. On a TS diagram, isentropic compression or a reversible adiabatic process. Whereas in case of actual process, it is not isentropic process. There is deviation from the ideal cycle during that process, number one. And second thing is, if you see, and this is the superheating, 1 to 1 dash is the superheating. So the actual, if you see the dash line, it is not, especially process 4 to 1 solid line, it is perpendicular to y-axis. That is isobaric. But 4 to this, similarly the process 4 to 1 corresponding to the dash line, it is slightly inclined. That means it is not isobaric. It is not isobaric. So there is a variation in the pressure. There is pressure drop. There is a pressure drop. So why the actual cycle process 4 to 1, the dash line is not perpendicular to the y-axis, which is the pressure, whereas the ideal case, this is perpendicular, this is the ideal one, which is perpendicular to this one, isobaric, perfect isobaric process. So if you see the reasons for the deviation, reasons for the deviation of actual cycle from ideal cycle. So if you see pressure drop in suction wall and suction line. So what happens? It is always desirable to have smaller pressure drop in this suction line. Otherwise, what will happen if the pressure drop is more? If the pressure drop is more, then the work of compression, the power required to raise the pressure and the temperature of the refrigerant from evaporator pressure to condenser pressure by the compressor, it requires a significant amount of work. So, and the discharge temperature, obviously it will be very, very high. Discharge temperature will be very, very high. And there are chances of the compressor life getting affected. The compressor may get damaged. I forgot to tell one advantage of superheating. The superheating process, which we have discussed just before making this comparison, it will ensure that only refrigerant vapor enters the compressor, because the compressors are designed for handling gases and vapors and not for liquids. So the superheating, few degrees of superheating, which is desirable, will ensure that the refrigerant vapor is completely vapor when it is entering the compressor, and there are no carryover of liquid. No carryover of liquid. Now coming to this one, and if the pressure drop in the suction line is high, so then the work of compression will be more, the discharge, the specific volume at the inlet of the compressor will be more, a specific volume, that is the reciprocal of density. If it is more, then the discharge temperature, the work of the compression ratio, the work of compression will be more. So as much as possible, the pressure drop in the suction line should be as small as possible. And heat transfer, second reason is heat transfer with the environment. To minimize this one, the suction lines are insulated. The suction lines are insulated in order to minimize the heat transfer by the working fluid with the surrounding or the environment. Of course, there are pressure drop in the discharge line also. You can see the diagram, process 2 to 3, which is the isobaric heat rejection process. If you take the solid line is perpendicular to the y-axis, whereas the dotted line, it is slightly inclined. So this is due to the variation in the pressure. This is due to the pressure drop on the higher side. That is the pressure drop in the discharge line. To summarize, in this lecture, we have seen, in lecture number 4, we have seen how the conventional vapor compression refrigeration cycle is been modified. So there are two technical aspects which we have discussed. One is subcooling, another one is superheating. And of course, we have seen the combination of subcooling and superheating. And at the last, we have seen the comparison, how the actual cycle deviates from the ideal cycle. The compression is not isentropic. There are pressure drop in the suction line, in the discharge line. The heat transfer, there are heat transfer between the refrigerant and the environment. To minimize this, the suction line is insulated. So these are all the reasons for the deviation of the actual cycle from the ideal cycle. So with this, I will complete this lecture at this point. Continue in the next lecture. Thank you.